Okay, we're going to start the last symposium for today. So the title of the symposium is The Development of Attention, Interactions of Higher and Lower Level Systems in Infants and Children. And our first speaker is Lauren Emberson.
Hello. Can everyone hear me okay? Yeah? All right. Thanks very much. Thanks, Jean-Rémy, for putting this symposium together, for the invitation to come, to the organizers of this incredible conference. And today, I'm here to talk to you about perception. So I'm mostly a perceptual scientist. I look at perception in relation to learning. So a bit more low level than a lot of the topics in this particular conference. But it's very relevant to the symposium topic because my work has come to be very interested in whether or not higher level systems are influencing and modifying perceptual systems starting early on in life. So again, my broader question is, how do perceptual systems become tuned to the environment? And by and large, we've thought about two potential mechanisms by which this might occur in the past. So one would be a passive bottom-up accumulation of experience on one hand, or maturational constraints on the other. And I'm not going to mediate between either of these. I think there's good evidence for both. But I will say that this is a model that by and large is inspired, especially the passive bottom-up accumulation by Hubel and Wiesel, and the idea that there's this kind of bean counting that might happen on the part of perceptual systems as they tend to bias towards input that they receive more often and against input they receive less often. But another idea that I want to propose here is that, in fact, experience could be influencing perceptual systems in a different way. And that could be through the combination of both bottom-up, but also what I'll refer to as top-down influences. Now, I want to be clear that I'm not using the word top-down in the Firestone and Scholl sense of, say, a volitional, conscious change in perception. In fact, this is a bit of an orthogonal definition of top-down coming from more of a neuroscience literature, meaning feedback connections. Those are connections from higher-level brain regions to lower-level brain regions, which would allow the influence of systems like learning and memory systems on perceptual systems. So I'm not making a claim about top-down in that particular way. I want to be clear about what my definition is. But in adults, we know that perceptual processing is modified by prediction through feedback or top-down connections. This is something there's been a great deal of work, particularly in the theory of predictive coding, but not exclusively there, arguing for this. But there's a large question about whether or not this capacity would be available to infants. And that comes by and large from a lot of work looking at the connectivity early in development. And that literature over the last decade or so has really said that the infant brain is very disconnected. It doesn't have these long-range connections. And in fact, feed-forward connections develop first and feedback connections develop later. So from that literature, we really think that this type of influence from higher level systems onto lower level systems should not be possible in infancy. However, starting as a postdoc, I decided to test this idea. And so the idea here is there might be top-down sensory predictions using feedback neural connections to modify perceptual processing. So this work started with some neural evidence, both from myself and Sid Crudier, among others, showing that there was evidence that prediction modifies the visual system starting by 6 months of age. And I'm just going to illustrate from the data from myself, because I'm more familiar with it, and also because it's from younger babies, but this work is all convergent. So at 6 months, what we did was we presented babies with a novel audio-visual association. So they hear a sound, it predicts a visual event, they get a variety of repeated exposure to this particular audio-visual association, and then we give them the sound without the visual event. This is just a schematic of the task. And we know that babies care about this unexpected visual omission, particularly in the 2017 paper. We have some behavioral evidence to that end. Here's a baby showing you the what the F face, which I think is very cute. But crucially, what's happening neurally, and particularly we use NIRS to record what's happening in the occipital lobe or the visual system. And that's what I'm going to show you here. The vertical axis is oxygenated hemoglobin, so that's our proxy for neural activity. More oxygenated hemoglobin, more neural activity in two different regions of interest, the temporal lobe, which we're using as a proxy for the auditory system, and the occipital lobe, which we're using as a proxy for the visual system. Now, starting with a sanity check, when babies hear the sound and they see the visual event, we get strong activity in both the temporal lobe and the occipital lobe, suggesting that we're picking up on both auditory responses and visual responses, as we should. But what happens when babies hear the sound and they unexpectedly don't see the visual event? Well, we see both temporal lobe activity and we also see very strong occipital lobe activity. In fact, it's not differentiable from the occipital lobe activity we see when babies actually see the visual event. But I'd like us to compare what happens with a separate group of babies in a control experiment where they got similar experience with both the auditory event and the visual event, but now they're always separate. So now when they hear the auditory event, they shouldn't expect the visual event, or at least it allows us to test, is this the case? Is it just obligatory for babies to activate their visual system when they hear the sound? The answer is no. So when they don't learn to expect the visual event, this is an expected omission, we don't see strong activity in the occipital lobe. And to me, this graph is particularly striking in the comparison of the occipital lobe on the far right to the middle, saying that the few minutes of experience in the lab changes the profile of this response from relatively low baseline response to a much greater response, suggesting there's a high degree of flexibility in the perceptual systems, even in quite young babies. So we went on to actually test the question of flexibility behaviorally. And in fact, a lot of our recent work is behavioral because I think it's important to constrain interpretations, particularly from neural results. I think these are suggestive of differences in perceptual processing, but I really want to see this play out in a behavioral task to be sure this isn't, say, error processing or something that's sort of epiphenomenal. And this is something that actually influences how babies act in the world. So this is work with my former postdoc and now just started as a faculty member at McMaster University, Gabriel Zhao. How flexible is infants' perception? And to do this, we actually turned to motion perception just for sort of ease of quantifying perception on single trials. And I'll show you what our trials looked like. They start with a shape that pops up on the screen. Babies look at that shape and that triggers an auditory sequence as well as motion perception. I'll show you what it looks like. This is a 60% coherence case, so a high degree of motion. Okay. So they see that sphere, they look at it, and it triggers the melody and then a particular direction of motion. We have another cue, a different visual cue and a different auditory cue that triggers a different direction of motion. And similar to the neuroimaging experiment, babies get a period of familiarization of this that's quite similar, and then we go on to test what happens in a crucial case. I'm going to skip through this. Let me say before I get to the crucial case that how we sort of quantified motion on every trial. So here's an intuition of how you can quantify motion on a single trial with babies. So this is looking at an eye tracking trace. And on the top graph here, what you see is the horizontal coordinates over time. And you can see that there's this drift, particularly in the blue portions, to a particular direction of motion. And these are going to be smooth pursuit eye movements. These are not saccades. They're from the electrophysiology data. This really suggests MT activity or activity in the visual motion perception areas of the brain. And we use a variety of methods to quantify how strong, as well as the direction of motion on every single trial. Here's one where we take the derivative and get rid of outliers. We also filter to the particular velocity of motion that we have, in this case, 8 degrees, visual degrees per second. Okay. All right, so now we can test in this particular case with 0% coherence, where babies are going to have some expectation for the direction of motion, but we're not actually going to give them a direction of motion. It's going to be ambiguous. So there's no available motion here. From a perspective of the bottom-up signal or the sensory input, there should be no bias towards one direction or another. However, if their expectations are biasing them towards a direction or another, we might see some of this potential eye movements that index motion perception in this case. Okay, so what do we see? Well, starting from the 60% coherence case, what you can see is that our indexing of the direction of motion is very good. I've never seen error bars on a baby study like this. This is with 20 infants. Doesn't this make everyone want to study motion? It made me want to study motion, which is why I'm going to show you 4 experiments. 60% coherence, this is what it looks like. But 0% coherence, this is what we see. So we still see evidence of direction of motion, and it differentiates across the left and right cue, even though the bottom-up input across these trials is identical, suggesting it's baby's expectations or predictions about motion that are biasing motion perception in this case. And incidentally, we never see differences between leftward and rightward directions of motion, so we're going to collapse across them and simply look at the absolute magnitude, which will look something like this. So based on that, now I'm going to compare what happens in a group of infants where we make these cues non-predictive of the direction of motion. They still see the cues, but now half the time they predict leftward, half the time we predict rightward, and that allows us to do some psychophysics. So we can take a look at, for our particular way of quantifying motion, how strong is our measure of motion across these different percentages of dots moving in a coherent direction, from 0, which is our test case, to 60%, which is our validation case. And it goes from 0 all the way up to 60. This is the non-predictive cue. Now, if we overlay the predictive cue on top of this, what we see is that there's no difference at the 60% case, which I'm happy to talk about if people are interested, but there's a significant effect from 0%, again suggesting that this predictive cue is having an influence on motion perception in that particular level. Across a number of experiments now, these are the first two I presented, we went on in experiment 3 to do a control for motor conditioning. So is it the case that when they hear the sound, their eyes just move in a particular direction, in which case this should not be sensitive to the perceptual characteristics of the input they're receiving? So what we did was we presented the cue and then static dots, so nothing on the screen. So is this an obligatory motor response? The answer is no. So you still see a strong response in the 60% case, and you see no response in the 0% case. Because now that we've done the thing where we show the effect and we make it go away, we wanted to make it come back again to show that we can replicate this effect. And in fact, we did that in a more stringent case where now only the auditory sequence is predictive of the direction of motion. The visual is not, to show that it's the auditory event cueing the visual. And again, we see, that's the fourth one there. Again, we see a very strong response to 60%. Look at how beautifully consistent that is. And we do get a response when, in that particular case, the cue is predictive, just the auditory cue. So now we both have neural and behavioral evidence. These are a number of other experiments we've done. We've done a bunch of work in face perception, which is Dr. Zhao's area of expertise, including looking at the face-to-face illusion, as well as temporal face perception. We've done some work in sentence comprehension as well, suggesting that prediction is a very strong influencer of perception early in life. Just to highlight the emotion face perception, this is where babies will hear, for example, a happy sound, and then we show evidence that they better perceive a happy face. And that's in a cognition paper, so you're welcome to check that out. It's already out. But we've tried to push this further. So I have to say I was completely surprised to find these effects as 6-month-olds when I did the original neuroimaging study. And so I convinced a number of people, including Dr. Zhao, to do a neonatal study to show that neonates do not do this. So here's a picture of one of our first participants in our neonatal study. It's qualitatively similar to what we did before, where they learn an audiovisual pairing. In this case, it's the syllable pa predicting a flash of light, since these babies are sleeping. And I'll show you this preliminary data now. So on the top, we have the occipital responses when babies hear the sound and it predicts the visual event. That's the time course, and then on the right is the averaged response over an a priori determined time window. And you see an occipital response when they hear the sound and they see the visual event. How about when they hear the sound and they don't see the visual event? Well, we continue to see a strong occipital response, similar to what we saw in the 6-month-olds. And what about if, and this is in a smaller group, this is why this is preliminary, we've now expanded this to a full sample but haven't not yet analyzed it. What happens in a control group where they hear the sound, they don't see the visual event, but they never learn the auditory visual pairing? Well, in this preliminary sample, we don't see a response. So qualitatively, this is the same as what we see in the 6-month-olds, suggesting that in the first 48 hours after birth, babies have this type of availability, of flexibility to their visual systems, even though they haven't received a lot of detailed visual input yet, suggesting this might be part of the machinery that babies come into the world with. All right, so So this to me is suggesting that despite what we know about neural connectivity from the neuroimaging literature, that babies actually do have a lot of available connectivity. And a lot of the sophisticated types of cognition, as well as tracking information over time that we know now more and more that babies are capable of, is something that is able to flexibly modulate how they interpret this input to begin with. I'm sure there's some boundaries to this. I have not yet found them. We're starting to apply this work in individual domains to try to understand how this might play out in the context of, for example, face perception. So, to summarize, top-down sensory prediction modifies perceptual processing in this new data as early as birth. It makes perception highly flexible and sensitive to the structure of the environment. Are these top-down attentional effects? None of the work that I've presented suggests that they are incompatible with that. I think, in fact, the motion perception work suggests that it could be an attentional effect, similar to classic models of attention where you have an upward weighting of information consistent with predictions and downward weighting of information that's not. But the debate about is prediction just attention is something that continues in the adult literature, and there's no resolution there either. All right, and also to say that this work is also consistent to some extent with really nice recent theoretical work by Julie Marquand and Lisa Scott, suggesting that there are influences, higher level influences of attention on the development of face perception. I think is really, really lovely work and worthwhile checking out. So thank you to everyone who helped make this work possible, the granting agencies, Dr. Zhao and Claire Robertson, who were essential for all of this, Claire in particular for the neonatal work. And also just to plug Dr. Zhao, he's, like I said, just started at McMaster University as of about 2 weeks ago, and he is recruiting prospective grad students for 2021, in case you know a really talented undergraduate interested in these sort of questions, also relatedly development of face perception. Thank you so much.
We have time for 2 questions. Luca?
Thank you very much. Very interesting. My question is a fact question that might come from ignorance.
Okay.
So in the motion perception, you code the rate of displacement. Mm-hmm. Yes. And this is a smooth pursuit. In principle, this comes from the, yeah. My understanding was that this requires a stimulus to be generated. In other words, that it's not like simple, maybe I'm wrong, but you need to have something. So the question here is, do you think that infants somewhat have an illusion of movement, or do you have a model which says, no, you can in certain cases have smooth pursuits in the absence of a stimulus? Because I would have expected that if it is real anticipation per se, you have saccading or whatever, but not smooth pursuit.
Yeah. Okay, so let me summarize the question. In the case where, in the motion perception case where babies hear the predictive cue and then you see this elicitation of motion, is an illusion where they perceive motion, or is this something about an anticipation in the absence of motion? Yeah, this is a great question. And this largely relates to the semantics. Let me go back to that slide of what I'm saying here. Thank you. It'll allow me to clarify. So what I think is happening here is that this is about the relationship between the prediction and the sensory input. I think that the prediction, or any of these signals that you're getting from these feedback connections, are helping to interpret the sensory input in the case where the sensory input is ambiguous. So what we believe at this point, although I have to say it'd be hard-pressed to really conclusively argue against, either for or against, but our current working hypothesis is that this is actually a bit of an illusion, right? So they are, in fact, seeing motion, and it's the combination of this top-down or feedback signal and bottom-up signal that produces that. I don't think this is anticipation because, particularly in experiment 3, that's where we should see the effect, where they get the cue and they don't get the bottom-up signal. There's no opportunity to combine that cue with an appropriately ambiguous stimulus. We don't see this. So I don't think it's the anticipation on its own. I think it's the combination of the two. I also have an infancy paper where we tested the purely illusory hypothesis. It's called How Visual is Visual Prediction. The answer there is very firmly no. We don't see that babies just confabulate a signal just from the predictive cue on itself. We tested it in a very different way using sort of preferential looking. So different paradigm, but that's our working hypothesis at the moment.
Thank you. So our next speaker now, François Leroy.
c'est lequel que... Good evening, everyone. This is my second experiment in attentional blink in infants. At the end of the first experiment, I had very promising results, but I had too many conditions and I didn't get good statistics. So we simplified the design. We acquired new data last year, and I thought it would be simply, I would have simply to rerun the analysis and I will get the same results. Unfortunately, I don't. I have some result in eye tracking, but not in electrophysiology. Instead, I would like to take the opportunity to talk to you about a friend and colleague with whom I collaborated in this experiment. So, if I may, I would like to pay a short tribute to Sébastien Marty, who died exactly 1 year ago. He got a brain tumor, and he was in his 40s and left 2 young children. So he was in our lab for 10 years. He was very enthusiastic and very helpful. And you can see on the right side a very nice picture made by an artist who knew him. And I can recognize his figure. And I know he loves stars as much as he loves the brain. So one of his main interests was related to the mechanism of attention and consciousness. So I pick up a few publications of him that you can see here, and I would like to give you a flavor of his work. Most of his work is based on this dual task paradigm in adults, where he presented a rapid serial visual stream with random letters, one every 100 milliseconds. And during this stream, there were 2 tasks. So an auditory task where there is a decision between a low or high pitch, and then there is a lag. And a second task, which is a visual task, is this a Y or Z? And the critical parameter here is the lag, so what we will call the SOA. And then he was recording the reaction time for each task, and also asking verbal reports at the end of each trial. And because he was an expert in magnetoencephalography, he used quite powerful techniques to decode the mental, the unfolding of events. So two important results was that, as you can see on the left part, so when you look at the blue curve, so meaning the number of correct response to T1, there is no effect of the lag of SOA. The curve is flat. But when you look at the red curve, for short SOA, there is a drop of performance. So there are trials that are missed. That's what we call the attentional blink. And then on the right side, this time when looking at reaction time, So the same for T1. It's the same reaction time for every SOA. But when you look at the red curve, so there is a sharp increase in reaction time for short delay, for short SOA. And that's what we call the psychological refractory period. So it's just, T2 is processed with a larger delay for short SOA. I think it was among the first one to show these two effects, these two phenomena in the same experiment, which it was able to suggest that they might refer to the same mechanism that we call the central bottleneck, that I will detail a little bit later. Just before going to show his nice results, I would like just to make a point on the technique he was using a lot, that we call decoding brain patterns in magnetoencephalography. So it's a technique that was used before in fMRI, and then 10 years ago, it was applied to MEG. And now it's been applied to EEG. So the idea is, let's say you want to discriminate between two mental representations at a given time point. But what I mean by a mental representation here is topography of dipoles at the sensor level. So you will have, let's say, as you can see, two topographies, one average topography for target, one average topography for distractor, and you simply build a classifier that can discriminate between the target and the distractor. And so the classifier will learn these topographies. You will go outside of the interference between T1 and T2 because you want to focus on T2. So you would use a long SOA, and then and then you would test the classifier at short SOA to see what you can decode. Now, if you can decode, so if the classification performance is above chance level at the same time points, you can say, well, yes, so the mental representation of the target is there in the brain at that time. And what is powerful is that you can also look at generalization a long time. So if you see that this classification performance is above chance level after T0, after these time points for a certain amount of time, then you can say, well, yes, the mental representation, well, it suggests that the mental representation of the target is there in the brain for this amount of time. Okay, so now let's go back to this study of the unfolding of events from stimulus onset to the conscious perception of the stimulus. He was able to decompose this unfolding of events in 3 stages. So the first stage is a sensory stage, which lasts approximately 200 milliseconds. As you can see on this figure, so that's the decoding performance for each stimulus in the visual stream. So here you have, let's say, 12 stimuli. And you see the decoding performance is about the same for each stimulus. Whatever the target, whatever the distractor, if the distractor is close to the target or far from the target, the decoding performance is the same, suggesting that it's really a parallel processing. Now, if you look at 200 milliseconds and you look at the decoding performance according to SOA, you see that the decoding performance, whatever the SOA, so the lag between the T1 and T2, is about the same. So it's the colored curves, sorry. And even if you look at trials that will be missed, so the blink trials, is the black curve, the decoding performance is the same, suggesting that during this window, there is no interference between the two tasks. Then you have the critical stage, which is the interference between T1 and T2 processing, which lasts approximately the same amount of time. There you see a strong effect of T1 on T2 performance. As you can see here on source reconstruction on the brain, you can see that on the left, the activity is much higher than on the right when the trials are blinked, so are missed. Then a little bit later, at 400 milliseconds, if you look at the black curve, the decoding performance gets to 0. So it seems that the mental representation of the target has vanished. For the trials where the target will be seen, so the colored curve, you see that it's a little bit different. The onset is the same, but the level of performance is not the same according to SOA. You have a strong effect of T1 on T2. There is, when the SOA gets shorter, then the decoding performance gets lower, but gets longer in time. So it's like there is a diffuse, an effect of diffuse mental representation during this time period for the target, which may explain this psychological refractory period where there is a delay in processing T2. And finally, the last stage is the conscious stage. And Sébastien assessed this stage by using verbal reports. And he asked the subject, what is the duration of the visual task? So he compared the objective reaction time to the subjective reaction time. So if you look at the red curve, you have the psychological refractory period. So for short SOA, you have an increase of the reaction time. But if you look at the green curve, which is the subjective reaction time, it's flat. So as if the subject does not see that his response are delayed. And he went a little bit further, by giving a kind of global picture of the unfolding of events from a conscious perspective. So first by asking, what is the duration of your auditory decision? So that's the black bar. And then asking a little bit trickier question about, according to you, do you think that the letter, so the letter is the visual task, occurs before or after your auditory decision? And what's amazing is that subjects always says, well, almost always says that the letter occurs at the same time or later, but almost never before, as if they did not have conscious access or some perception of that the T2 was being processed in their brain. So that's what we could call the blind spot of consciousness. But finally, all these results fit nicely with the global workspace model of consciousness. You may know that Sébastien and myself are in a lab headed by Stan Dehaan. And Stan Dehaan is a key contributor to this model of consciousness. In this model, consciousness is seen as a global availability of information. So meaning that once information enters a global workspace, that would be the stage of consciousness, it allows the sensory information to be routed to some new intention, or to be manipulated in a complex way, or to be verbally reported. The workspace, the global workspace is not anatomically very clear, to be honest, but it involves prefrontal cortex, long-range connections, and it's a very dynamic, very changing all the time. A strong hypothesis about this model is this bottleneck. So, meaning that when information can enter this global workspace only through this bottleneck. So the brain is constantly bombarded by stimuli, so they are processed in parallel in the early stage, but at some point it has to be serial. So only one information will enter this global workspace. The other information will either have to wait or simply vanish. And I think the work of Sébastien helped to confirm this theory. So I will be very brief about my own experiment, just to give you a hint about it. So there are two tasks. The first task is a passive viewing of a teddy bear. And there is a second task, which is a face discrimination, with a face appearing either on the right or on the left side. And between them, the lag, so it's the SOA of 400, 800, or 1,200 milliseconds. My results up to now, I hope to show you better results the following time, I don't know, or another time, is that only at the longest SOA, so 1,200 milliseconds, I have the infant is able to do some phase discrimination when I'm analyzing the saccadic eye movements. And also, I found a greater pupil dilation in trials with Q compared to trials without Q. These results fit with this graphic that I show, where there is a drop of performance at short SOA. And the fact that phase discrimination is quite a high-level process, and also that it requires an increase of attentional resource as shown by pupil dilation, suggests that this result fits nicely with the idea of an attentional blink, let's say of approximately 1 second in these 3.5-month-old infants. Thank you for your attention.
So maybe we can take a very short question.
Thank you for the two things you did, the talk and your recollection of your colleague. It was very, very touching. Just a small question. If I remember well, in the face discrimination experiments, face literature in infants, very often you don't use this kind of stimuli. They're very complex stimuli, but you use very simplified stimuli. My question is, do you think that this kind of high cost in processing faces is really dependent on the fact that you are actually showing real pictures as opposed to just, say, for example, schematic?
So we chose the scramble. So you see the scramble face. So it's just the same face, but with rotated mouth, eyes, and so on. It's inspired from the work of Turati, where she showed that 3-month-old infants are able to do this discrimination. We wanted to console as much as possible any low-level feature that could explain this discrimination. I think we are quite close to it because it's exactly the same low-level features if you look at the mouth of the eyes. And I must say, to go in your direction, that's, of course, the performance is not very high. It's significant, so I measure the D prime, which is, in signal detection, you use the probability of detection of the face and you compare it to the probability of the false alarm being the saccade towards the scrambled face. And the D prime is only positive for the longest SOA. And what I didn't say is that it's only when the face are on the left side. And it goes with, if you remember, Parvane did a presentation 1 hour ago, and but before moving to Lyon, she was studying face perception in infants, and she also showed that face discrimination and not face detection involves the right hemisphere. So it's when the face are on the left hemisphere that the infant can discriminate between two very close and similar stimuli, face-like stimuli.
Thank you very much. All right, thank you very much, François. So the project I'm going to present now is really in line with what François presented, as you can see from the title, An Attentional Blink and Infancy. And in fact, it's great to present this work here because this work was born exactly 2 years ago at the social dinner of the BCCCD 2018 in a discussion with Sid Quider, and then later on Parvane joined on the project. So, as François very well explained, attention is limited in adults, and to be very brief, it's limited to process one stimulus at a time, and it's very, so one typical effect that shows this is the attentional blink. And so a classic paradigm that shows this, very briefly again, is this one, so where you present letters at a fast rate, so for instance, you present numbers 100 milliseconds each, and in the midst of these numbers, there are 2 letters, and the task of the participants is to report the 2 letters that they've seen. And so, again, as François explained, the typical result is that the first letter is well reported. The second letter is well reported if it occurs late, that is here around 800 milliseconds after T1. And on the contrary, it is often missed if it occurs around 200, 300 milliseconds after the first one. And so the attentional blink is measured this way. That is the difference of report between late lags and the lag 2-3. But here there's also a second phenomenon that you might see, that is that when the second letter appears just after the first one, both are actually well reported. It's called lag 1 sparing. So those are 2 effects that often come together, but not always. And to be completely honest, I don't fully, so I'm sure there are people who fully understand. I don't fully understand when it comes and when it doesn't. So my predictions about the lag 1 sparing are a bit shady. This behavioral effect, the attentional blink, again, is very well explained by models, by hierarchical models of the brain and cognition. And so the idea, again, is that high-level systems are busy processing T1 when T2 comes, and therefore they cannot take T2 in. And an interesting finding from recent imaging literatures is that the hierarchical organization of the brain might be in place actually very early on in infancy, if not already at birth. So the questions we wanted to address in this project is first whether this organization is actually functional, and so we would take the attentional blink as a behavioral signature of this architecture. And second, we wanted to see the temporal dynamics of attention and their development in infancy. So I don't have to explain people in this room that we cannot ask infants to track letters in the midst of numbers. So instead, what we're going to do is, just like François, try to use their propensity to look at faces. So here's the way we did this. So we have infants sitting on their parents' lap in front of an eye tracker, and there will be 2 locations on the screen where pictures can appear. Most of these pictures, as you can see, are just masks. And in the middle of this picture, well, some of these pictures, 2 of these pictures are going to be faces. So let me just show you directly what infants actually see. So it's shaking because I'm shaking, right? It's not shaking for infants. So what you can see is that, so that's one trial. Next trial, so there's a face that will appear in the middle and then a face here on the left. Then that face is going to come back at the end, so that in the case infants don't see anything, we're still telling them there is a face that's going to appear somewhere. Okay, so this is what they see. So more precisely, again, there are 3 locations on the screen. A face appears first in the middle, and then there's another face that can appear left or right, and what we're going to vary is the time between the 2 faces. Each picture appears for exactly 300 milliseconds. So the second phase can appear just after the first one. Those are the lag 1 trials. It can appear left or right. Or it can appear at lag 3, that is the third picture after the first phase. In this case, they appear around 900 milliseconds. And again, they can appear left or right. Or they can appear much later, that is as the 7th picture. So here, around 2100 milliseconds. And again, left or right. And so the idea is that if infants see the second phase, they're going to gaze in that direction. And so what we're going to measure is whether infants tend to look left or right. So those are the results. So here we tested 5 months old. And let's start with the latest lag, so the lag 7. So here you have the appearance of the first phase between these 2 dotted lines. And then the second phase is appearing here, that is 2 seconds and 100 milliseconds later. In blue, you have the proportion of trials where infants look toward the correct side. In red, the proportion of trials where they look toward the incorrect side. And so what you can see is that infants tend to look more often toward the correct side, suggesting that they have seen the face in these trials. But in like 3 trials, so that is when the second phase appears around 900 millisecond trials, infants do not show any evidence of seeing the face. And finally, in lag 1 trials, here we do see a trace of detection. Infants tend to look in the correct direction. So this absence of detection here, as compared to the presence of detection in like 7 trials, is what we would call is a signature of the attentional blink. And we also measure the difference scores. That is the difference between looking time towards the correct and incorrect side, and show that it is difference between the lag 7 and lag 3 trials. So those results suggest that 5-month-olds do exhibit an attentional blink in infancy, and that it seems to be here around 900 milliseconds. So that's very compatible with what François just presented. There's one caveat in this data, which is, let me first say that we also see here lag 1 sparing, which is interesting, but I don't have much to say about it. So one caveat about this data at this point is that we haven't formally shown that the blink is due to the processing of T1, because we haven't played with the presence or absence of T1. That being said, what we do is to ensure that, so we keep only trials where infants do look at the center when the face appears in the center. And so I have trouble imagining that infants will not be processing the face that they look at for 300 milliseconds, that they fixate for 300 milliseconds. That being said, we haven't formally tested that yet. So at this point, with this caveat in mind, I think we do show that 5-month-olds exhibit an attentional blink around 900 milliseconds. And that's much longer than what is typically observed in adults, where the attentional blink is observed around 300 milliseconds. So that triggered the next question, which is to investigate the development of the attentional blink and, more precisely, the shrinking of the attentional blink. So in the very same paradigm where we tested 5-month-olds, so still with 300 millisecond presentations, we also tested 8-month-olds and 12-month-olds. And here, the pattern is quite different because faces were very well detected at all lags that we tested. So we thought that here there are 2 things that could be happening. First, maybe already at 8 months, maybe the attentional blink has shrunk, and so we are missing the attentional blink here. And the second possibility is that 300 millisecond presentations are just too easy for 8 and 12-month-olds, and the padding needs to be hard enough for the attentional blink to be observed. So what we decided to do is to make things more difficult by simply accelerating everything. So everything remains exactly the same, but instead of presenting pictures for 300 milliseconds each, we present them for 200 milliseconds each. Okay. So now lag 1 trials at 200 milliseconds, lag 3 at 600 milliseconds, and lag 7 at 1400 milliseconds. And we did not complete this group. We actually stopped after 13 subjects here because what we saw is that they were going to detect very well the faces at each lag. So instead of completing the group, we will complete it later. We decided to accelerate again the tempo, and now we present each picture for 100 milliseconds. So now we are actually at the type of presentation that are used with adults. So now lag 1 trials are at 100 milliseconds, lag 3 at 300 milliseconds, and lag 7 at 700 milliseconds. And what we observe now is correct detection at 700 milliseconds, so down there, but no detection at lag 1 and lag 3, so there's until 300 milliseconds. So that suggests an attentional blink in 8 and 12 months old. By the way, I've put together the 2 age groups just to have sufficient number. At this point, we don't see any difference between the 8 months old and the 12 months old. So we do find, again, an attentional blink here with 8 and 12 months old. So let me get to the conclusions. So we did observe an attentional blink in infancy from 5 to 12 months old. And I take this as a behavioral signature of the hierarchical structure of information processing in the mind and the brain. But what we observe also that is quite interesting is this shrinking of the blink in development. So again, at 5 months, we do observe a blink that is around 900 milliseconds. We don't know until when it lasts, right? We just know it's gone at 2100 milliseconds. And François' results suggest that it's gone at 1200 milliseconds, though with younger infants. So in any case, it seems to be around 900 milliseconds. But already at 8 months, we see that it's much shorter. So at 700 milliseconds, there's no problem in detecting the faces, and the blink, therefore, cannot exceed here the 700. And let me show you what this means, because, so let me show you the 2 types of presentation that we use. So if I can, okay. So this is what I just showed you earlier. This is what posed problems to 5 months old, right? But absolutely no problem for 8 months old. In contrast, this is what gives the same level of difficulty, if you want, for 8 months old, right? So it's much, much faster. And that suggests really a huge acceleration of information processing, at least visual information processing, in between 5 and 8 months. So at this point, the next step is to try to understand what's changing between 5 and 8 months. There seem to be important maturational processes. And again, referring to imaging literature, especially the work of Jessica Dubois, it suggests that indeed there's a lot of myelination happening between 5 and 8 months, and particular in terms of the communication, maybe between occipital and frontoparietal areas. So the next step would be to try to relate these 2 effects. Thank you. Okay, maybe one question.
I'm so glad that you showed the stimuli for the 100 millisecond and the 300 millisecond. Because what I noticed was that, is this on? Oh.
Yeah, you need to speak loud.
Okay. I'm so glad you showed the stimuli that was sped up. It was much easier for me, much easier. I got a pop-out effect for the faces relative to the 300 millisecond stimuli, and I don't know if anyone else felt this phenomenon. But probably what's going on is instead of trying to fixate and make saccades to each individual stimulus, what you're doing is a sort of, it's just so much easier for me. It's probably easier for adults, just going on my own intuition. So you're doing a more holistic, global processing instead of trying to infer details. So I guess it just makes me a little bit concerned that it's not about better processing, it's about strategies of processing and how they're changing with development. And sort of, yeah.
Yeah, that's interesting. So we're running an adult version of the task. I can show you the preliminary result. I'm not fully convinced that we've done that fully well, but so here we added one difficulty is that we variate whether the targets are faces or flowers. And the task of participants is to say whether T1 and T2 are from the same category. Okay, so face, flower, flower, or face, flower, flower, face. And the results that we get is this, but basically they see everything, well, they see faces very well. They have much more trouble with the flowers. But it suggests that when T1 is a face, there is a blink around 300 milliseconds. When T1 is a flower, we don't see any blink, which is fine. The idea is that T1 captures more, the face captures more attention than flowers. But yeah, I think we need to work a bit more on the adult part. Yeah, that being said, we haven't tried also the 100 millisecond with 5 months old. I don't know what would happen there. But 8 months old basically do the contrary of what your intuition is, right? They do better with 300 milliseconds than with 100 milliseconds. Okay, I think we need to move to the final talk. Thank you.